In this video, I would like to explain how to determine the direction of an induced current using Lenz's law. So Lenz's law states that the direction of any magnetically induced current, or EMF, is such to oppose the direction of the phenomena causing it. So let's take a look at an example below here. I'm just going to look at a magnet that is simply thrust into this loop of wire. Now, as the magnet is pushed into this loop of wire, what we find is that the magnetic field that is emanating from the magnet is increasing into the plane of the loop. Hence, we say the magnetic flux is increasing into the loop. Lenz's law requires that the induced magnetic field from this loop of wire, that you can see the current that's being induced, is such that it opposes the change of flux through the loop. So essentially, it creates its own magnetic field to oppose the motion or the change in flux. It's like it tries to keep everything in balance. If I push inwards with a magnet, it will essentially oppose this motion by pushing a flux out to keep things in status quo. With the induced magnetic field, there'll be an induced current, and the direction of the induced current is determined using Lenz's law. In this case, I prefer to use the right-hand rule, in which my fingers, in this case, curl in the direction of the current, and my thumb points in the direction of the induced field. Going back to our example, you can see that we have, as the magnet is being pushed inwards, you can see here is the earlier time with a few X's. It looks like we have about 6 field lines that are penetrating within the inside of that loop. And then as the magnet is thrust into the loop, we see more field lines that are penetrating in here. Sometimes I like to think of drawing in my field lines, something like this. I have a field line here, I have a field line here, and I have a field line here. But these field lines on the outside are not quite penetrating inside. So I'll draw, say, 3 X's going into the loop. And then as the magnet is closer in here, then I have more field lines that are penetrating inside the loop, and so I'll have simply more X's going inside the loop. And so this is another picture that you could show as well. Now, because I have more X's going in, the loop will then induce its own magnetic field going in the opposite direction. Often I'll show this in a different color. So it tries to keep things in balance and go back to, say, 6 field lines penetrating inwards, and it'll push these extra field lines out of the loop like this. So they're like little dots that are coming out of the plane of the loop. And then using the right-hand rule, if you remember up here, we have the right-hand rule with our thumb pointing in the direction of the induced magnetic field that is out of the plane of the page, and my fingers will curl in the direction of the current, which is going to be counterclockwise over here. And so my current goes counterclockwise in our picture. All right, go on to the next video where we'll talk about different conceptual examples.